Okay, so the last set of videos we basically built the logger stack, which is basically sort of a complete standalone unit. But to make a full deployable instrument, you need to add a lot more components, especially the batteries. And that's what we're going to talk about here, is the stage that takes your logger stack and turns it into something like that. So we're going to be adding the battery holders and the extensions, and in some cases these will be different depending on what you're connecting to your logger. So the simple version of that looks like this, and you can see I've got model written there because I always keep one handy just to remind myself how to build them. And so this is for a 2x4 AA bank of batteries, and I like having two banks of batteries, both for backup in case one set of cells fails, but also for units that draw a lot more power. And I think you said yours was going to run
on 2 banks of 4, yeah.
2 banks of 4 because you've got the Atlas conductivity board, and the conductivity boards always draw a lot of power, and so having a second set of batteries is really nice. The logger itself would run on 3 AAAs if you wanted, but not anywhere near enough.
How long would the logger itself run on just 3 AAAs?
Depends on your sleep current. Most of the students who've built these guys first time around end up with a sleep current of around 0.5 milliamp, and you get about 800, 900 milliamp hours out of a AAA. So just dividing that 1800 hours and divide that by 24, that's how many days of operating time you've got. Okay, so it depends on your sleep current. You know, as you build the more complicated versions, I talked about shutting down the SD card. So this one just has the SD card. Just has the SD card running right to power and ground, so there's no disconnect on the SD. But if you disconnect the SD, you move the current down. If you change the way the RTC is powered from the default, which is about 0.1 milliamp, to running it off of a pin power source, for example, again you pull off about 0.1 milliamps. So you can bring these loggers down to really low currents in the 0.03 range, and so one of those would run for 4 to 8 years on this many batteries. It depends really on what power optimization you did when you were building the logger itself. So yeah, like I said, most people are getting around 0.5 milliamp, between 1/4 and 0.5 milliamp on their first builds, and so you just divide that into the amp hours of your batteries. AA's are about 2,000 milliamp hours, so that would be about 4,000 hours on a 0.5 milliamp system. Okay, so to get started, we need to get our parts together. This is just a knockout cap that you'll find commonly available at plumbing and hardware stores. And the idea is that we use that platform as part of a housing. So the logger goes on this, and then it goes into one of these end caps, and then a rubber housing comes onto the bottom. So that's where we're headed, but we're basically going to start with just getting the logger powered on that plate. And we're going to need some battery connectors, battery holders rather, and some double-sided tape. And the idea is that we simply put double-sided tape on the back of these things, and then that's how we adhere it. So the first thing we want to do to go from that to that is cut this little tab off. These connectors, or rather these knockout caps, have a little tab that allows you to pull them out of the pipe when they're put in, but we don't want that. We need that space, so we're going to cut that off. It's pretty easy to do. Just carefully. You don't want to go through the plastic, you just want to disconnect that. And that leaves us with a little tab at the top, and we can actually use that as an indicator of our positioning. So I try and line everything up. With what's left of that tab so that I know where I'm putting everything on the plate. There's also a little casting sprue there in the center as well. I'll take that out. Have to put some tape on the back of these guys. Pretty easy to do. This is the 5-pound outdoor mounting tape from 3M. It's usually strong enough, but occasionally you get battery connectors that are not very sticky, and so you can switch to the 10-pound.
What do you mean by the battery connectors are not very sticky?
Sometimes the surface, these plastic surfaces, sometimes this tape really won't stick. In fact, this is one of them. So let's grab the 10-pound tape for the back of this one, because this has got some sort of relief on it. It's the black outdoor mounting tape. This is the 5-pound is this gray tape, and I like it because it's removable. The black stuff, however, does a better job on plastic. Okay, so this is the 10-pound mounting tape. This is the 5-pound, and I use these both quite a bit when I'm putting the loggers together. I like the 5-pound for the logger stack because it is easily removed if you've made an error, but as I was demonstrating there, sometimes the plastic for these battery holders just will not stick to the 5-pound, so then you have to switch over and use the 10-pound tape.
Do you ever have to use more than 10-pound tape to get something to stay permanently?
No, usually it's okay, because once the loggers are together, you find that they tend to compress the tape. So as they age, the adhesion gets better. But when you're just putting it together, it doesn't hold sometimes. Again, it's kind of a surface effect. This plastic has sort of a pearly surface, and that's what's really preventing the tape from getting a good grip on it. Okay, so now we've got a couple of singles, a 4, and there's a double.
Why do you have different sized ones?
It just for arrangement. So let's take a look at that. This is basically just trying to fit everything onto the plate. So I'll move these out of the way here. What we're aiming for is something that leaves enough room for the logger and the batteries to fit onto this plate. And so this is why we end up with a couple of singles, a double, and over on the back, one bank of 4 and the single. The idea is we're just trying to make enough room in this limited space for everything to go together. Alright, so once we have all the tape on the back of the battery connectors, it's time to arrange the pieces. And I usually, as I said, I start with this as an indicator. And so it's hard to see on the camera because it's white, but there's a marker there, and I usually use that just to keep my alignment. Awkward here. Separate the backing from the double-sided tape. just going to cross right up against the
marking that you cut off.
marking that I cut off, so it's sort of at 90 degrees, and that also tells me where I want to have my other one on the other side. I want to have them kind of parallel to each other but on opposite sides of the board.
Okay. Do you want the wires opposite each other with the one on the other side, or?
Yeah, the polarity matters. I'm going to have the black on this side and the red on this side, and that makes sense later on.
Okay. And then the other side, so it's like the red and black are on the same sides.
Yeah, they're arranged opposite in space. So here it's positive and there it's negative on the opposite side, and that'll make sense because we're going to end up putting them all together in series.
Okay.
Okay, so we just try and arrange this so that it's pretty much the mirror image of the one on the other side. Stick that down. Okay, and the next one I put in is the double. The double gets arranged as close as we can get to the edge. Again, if we look at our model here, the wires are going to pass through from the bottom. And so the idea is we just want to leave as much room as possible for the logger without having your battery hang off the edge of the platform. And these are just cheap battery holders from eBay. I think they cost about 50 cents each. They're really not, they're not the best. If you want good battery holders, you know, spend a few bucks more and get ones from Keystone. I think Keystone, there's a few companies, Velman, they make really nice battery holders, but you pay through the nose for them.
And having quality battery holders, that just improves the ability for them to last, or?
Yeah, these ones tend to have really crappy metal. So if you look at this, I often see oxide building up. Even when the ones are new, you see these little connectors, and this is, you know, cheap little wires. So I often even use metal connectors. If we go back to this one, okay, you see this battery holder here. This is actually who makes this one again? I'm trying to remember. I think this is Keystone's. Yeah, Keystone Electronics. This is Keystone's metal series. They're really annoying to work with, though, because you have to solder all your wires on and everything like that, but they are bulletproof. In fact, sometimes they compress the batteries too much. I've been actually concerned that they're squeezing the batteries hard enough to actually hurt them. So the reason I went with metal on these ones is this logger series was being deployed in the cave, so they're really getting beat up on the way in. We had to rappel through a waterfall and do all sorts of other things, so they got bashed up a lot. So I was worried about these batteries on the top flipping loose while we were still trying to get out to the deployment site. On the back, you can see that I've still got the plastic ones, and that's because a rubber housing holds those in place. They couldn't possibly shake loose, but occasionally I'll shell out and get the really nice metal battery holders simply because I really want them to be secure. So, you know, there's a whole range. Like everything, you get what you pay for. Alright, so this, you know, just doing a spacing check, that looks good. You know, we got lots of room for the logger to go in there. And now we can just flip around and put the one on the back. Oop. See, even with the 10-pound, it's still having trouble sticking to this surface. Once it's deployed, though, I find that this 10-pound tape, it sticks better over time. I don't know if it's curing or what's actually happening, but it will get stronger. I mean, we've just put this on here, so it's not holding all that well, but it does hold well later. Let's just try tricky to get the backing off because, of course, the adhesive on the black 10-pound tape sticks to plastic well, right?
Mm-hmm.
And this is plastic backing. All right. And
does the orientation of the second 4-pack matter?
yes, the orientation matters on all of these. So you can see how where the leads are coming out.
Mm-hmm.
When we try and join everything together, we're going to actually put a diode in there to isolate these battery banks, but it does matter what the orientation is. And even leaving a little, I didn't quite leave enough space there, but occasionally it's nice to run wires around, so we're probably going to have to shift that. Unfortunately, I've already put it in place, so we'll just have to squish some wires there. I didn't see this side has a little air gap there,
Yeah.
and that lets you run wires through, and I put this too close. I should have had a little air gap there so I could put wires through. But it'll have to do. Okay, so that's the basic pieces in place, and then the next step is usually to drill the pass-through holes so we can start to solder all these pieces together. Alright. So this wire needs to pass through, so
Okay.
we're going to need a hole here. And not only does this wire have to go through the bottom, but another set has to come out, so we get another hole right about there. These guys have to go through to the bottom, so we need a pass-through hole there. And then, because we're going to be soldering a bunch of wires together on this side, when we do all of our joins to make this into one complete battery case, we kind of want some tie-down holes so we can run a zip tie through and tie that all together. So over here, I add a couple more. You want to be careful because we're drilling through something that already has something on the back, so you don't want to drill through and accidentally puncture the battery holder. So you have to sort of make sure that they're in the right place for both sides when you're marking these.
Mm-hmm.
And then the other holes that I usually put in have to do with how I route my cables. So when we put this guy in place, we're actually going to have wires coming out of the logger, and you want tie downs for that as well. So I'm just going to add another couple holes somewhere around here, and another set here, and these will be basically tie downs for the final cable routing. And on some loggers I also have cables coming out this end, and so I put a tie down here. Again, I want to make sure that I'm not drilling into my battery holder. If I flip this over, I don't want that to go through. So sometimes it's better to just sort of estimate where you are and mark on the other side. That way you're for sure not going to be putting a hole in your battery connector. So maybe these ones will drill through. So we're just going to go over to the drill now and put those through. Okay, so we've got the holes drilled through. We used a 5/32 bit here. There's a little bit of the ink left, and if you want to make your logger pretty, it's easy to remove Sharpie marks like that. A little isopropyl alcohol, and that's just go away. Eventually you start to care about whether it's pretty. The first few didn't look pretty. Let's just put it that way. Okay, so now we've got a set of holes, and we also made this one a bit bigger. These holes here were 5/32, and they don't have to be that large because they're just holding zip ties. But this one right here, we bumped that up to a 1/4 inch because there's going to be more wires popping through the hole here. That's where the battery connector is eventually going to come out of the whole plate. So that one's a little bit larger. Okay, so now it's time to start connecting things. And the idea is we bring some of these wires down through the plate from the top, because all the connections get made at the bottom of the plate. the first two that I join, again, remember this is one bank of 4, but this single at the bottom and these are all going to be connected in series to make our second bank of 4. So the first one that we connect are those two, okay, and that's the positive side of the one on the bottom and the negative side from the one on the top. So we can just cut and solder those. Okay, that's just a little bit of flux.
And that's just to protect it from making any unwanted connections?
Yeah, I mean, all of these connections should really be protected with some sort of heat shrink. Okay, so there's connection number 1. Connection number 2 joins the positive from this side all the way down to the negative. Alright, so the negative line from here connects to the positive wire from that top battery. Okay, so this gets to be a bit of a jumble. Connection number 2, positive from the top, negative from the 2-pack on the top.
And what does the flux do?
It removes oxidation from the surface of the metal. When metal becomes oxidized, basically rusting, the solder won't bond. It won't melt into the surface. When you solder things, you're actually creating alloys, and so the stuff actually becomes a new type of metal. And that chemical reaction, I guess mixing reaction, is not even a chemical reaction. The blending of the two metals into an alloy can't happen if there's a hard oxide layer on the outside. And so the flux is really, I believe it's acidic. I'd have to check. I can never remember these things. Basically just burns away that oxide layer, leaves some exposed metal, so that when the solder is on it, the solder can alloy into the surface of the metal. Okay, so there's
A little bit higher.
There's one of our connections. Okay, again we're putting those into in series, and the next one I typically do is I join the two ground lines. So this is the ground from the 4 battery, and this is the ground from this holder right here. But when they're all in series, this will be the ground for that whole set. So that one gets another wire. So I'm just gonna cut that. and bring another wire into play so that we can pass it through to the battery connector. I don't want this one to be too long here because we've only got so much length to go back up. So, and that's where I keep holding this. I'm comparing it to the location of the holes because that's where the zip tie will be that will hold all these cables together. So I just want it to go past the point where the holes are without making it too short. Okay. There's number 1, number 2, and wire number 3. So those will be the common ground line.
And that third wire is what will be able to connect to the logger.
Yeah, that'll go into a battery connector that's removable. I use connectors called mass connectors now. I've tried all sorts of battery connectors, but these seem to have a nice, trustworthy bond. They're a little annoying to open and close because they're quite hard, but you know, that's what you want. Again, some of my units get beat up, and so you want them to be securely together. Okay, so there's our ground. I'm going to put another heat shrink on that one just to see.
Why?
That one's a bit too small. Just to hold these wires together into a tighter bunch. I'm not sure I got that one exactly as I wanted it here.
Okay.
Okay, so here's a slightly larger heat shrink. Again, just to bind that bundle together. Probably not needed, but okay, so that's the common ground line, and that's going to go back up to the battery connector. So that one actually feeds back out. Yep. Okay, so series connection, common ground, and now that all of those individual battery holders are series connected together, what we have is the positive rail from this 4-pack, and this one right here is the positive rail from the ones that we just put in series. And we can't just connect them together and then run one back up to the top like we did with the ground line, because if we do that and the voltage is different from this bank of 4 than the bank with the separate holders, whichever bank has the higher voltage will push power backwards through the other batteries, and that will always do bad things. So what we have to do is somehow isolate these. They have to be connected, but we're going to isolate them with diodes. Diodes only let power go in one direction, and so to protect these two banks of batteries from each other, we're going to now make that diode interconnect, and then that'll allow us to feed one line up to the top of the logger.
Okay.
Alright, I use Schottky diodes for the battery isolation, and the reason I use Schottky diodes is that they have a very small voltage drop, so you don't lose any power, or you lose less power than you would with an ordinary diode. This in a bit here. Okay. These are 1N7s of 1N5817 actually, and when you're choosing diodes to do battery isolation, you want to choose one that has the right voltage range for the battery pack that you're trying to protect. I used to use 1N5819s, and they're rated up to 40 volts, but what that means is that the voltage drop across them is much larger and you lose more power through your diodes because they weren't matched to the range that you're trying to use. So basically just going to connect the output ends together, and again there's a line indicator here that tells you the direction current will flow. So you're putting the two lines together on this little isolator. I'm going to solder those together and then we will add the wires to them. So first we tin everything. And you don't want to add too much flux. Again, flux is corrosive, so if you have residue after this soldering process, then the residue will start to eat your circuits. So it's kind of a balancing act, getting the right amount. Okay, so that's, those two are now joined. And I'm holding these in my fingers for a reason. Even though it's slightly risky, it means that I'm not going to cook my components. I can kind of feel the heat being transmitted. Now it's getting a little annoying. But basically, if I can hold it in my hands, I'm not going to kill my component. The next part is a little tricky because we're going to have to sort of freehand the soldering, but basically the positive rail from each of our 4x AA battery packs will go to each of these two inputs, and that little addition will protect the banks from each other. Remember, I mentioned I wanted to leave a little space here, and I forgot, so we're just going to have to push these wires down there a bit.
And that won't damage the wires?
Not too much. I mean, they shouldn't. They're kind of bound in place there, so they shouldn't be too badly off. It's my own fault. I should have left a bit more space there. Alright, so there's our one positive rail, and again I sort of want the divider to get held down between those two holes, so I want it to be somewhere around there. So I'll just sort of hold it in place and do my wire cut where I can see all the parts together. When in doubt, leave it longer than you think it needs to be. And this one, from the bank of 4, that's this bank here, that's the positive rail, it has to sort of go down and then twist back to connect. So that one gets cut a little bit longer. Oops. I just I mashed some of my wire there. Good thing I left it longer. I did a bad job of stripping it.
About how much of the wire do you typically strip off of the casing?
Normally I'm trying to work... Oh, that's just really thin wire. I thought I had cut the wire by accident, but it turns out that's just a really crappy wire. That's what you get with these cheap battery holders. It's just a very incredibly thin wire. Somewhere between 1/4 inch and 5 millimeters. I know that doesn't help everyone who isn't ambidextrous with the metric and imperial, but you know, about that much is the typical amount. Anything longer and you end up with too much pokey bits inside your housing, and it tends to give you issues with shorts and things like that. And not enough, and it's hard to get a good solder joint on them. Okay, so I'm going to pre-tin each of these connections. Okay, before I bring them together, you always want to tin your wires. And you also have to remember to add your heat shrink to cover the connection, right? Because you don't want anything exposed that might cause these to connect with anything later. So you got to run some heat shrink along your wire as well. Alright, so now I'm going to hold this in the vise. Run some heat shrink over my wires here. Alright, so there's my isolated positive rails from the two banks, and that should just tuck in there. Run the wire through here, yep. I'm not doing the tidiest job of this because it's a little awkward with the camera and whatnot, but basically the idea is now, because we've got these holes here that you drilled on the other side of the platform, we just run a zip tie through and it just holds all the wires safely onto the platform. And we're going to do the same thing over here, but we'll do that later because those holes will do double duty. There'll be other wires on the surface, so when we run the zip tie through, it'll hold the surface connectors and that. So I'm not going to do that one straight away. We'll just do this one. Like I said, it's not the prettiest one I've ever done, but the excess. And now we have two wires, and we're going to put a connector on that and have another set of wires that goes down to the logger. Alright, so these are the battery connectors I usually use now. This is an Amass XT30U, and they have a really nice firm connection. In fact, it's actually quite hard to get them apart. But the thing I like about them, it's a little hard to see, but there's a four-way cut into the pins. And if you need to make these connections stronger again, you can just wedge a little screwdriver in there and push that split pin apart. And that way, when you put the connector on, it actually increases the amount of friction. And so when these connectors get old, it's really easy to sort of firm them up again just by wedging a very tiny screwdriver into that connector. So I've sort of switched over to these because I found that over time they age more gracefully than some of the other connectors that I was using. And the other thing about putting battery connectors into place, these have a really nice covers on them. You can see that it's very hard to have a touchdown on these exposed connectors. But a lot of other battery connector styles, one of the sides, or maybe both of them, usually the male pins, are exposed. And so if you have a piece of metal that just happens to make a touchdown, you can have a short circuit really easily. These are nicely protected, but I still stick with my rule of always use the female connector on the side that has power. And that's true of all the connections that I do on the logger. I always make sure that the side that's supplying the power is a female connector, so that you can't have those accidental touchdowns on any metal surface inside.
Does it matter which side you put the ground on, or just that they both line up? You put the ground on the same side and you put the...
It does matter. You want to be consistent in all your builds, and in fact these connectors have polarity indicators on them, so you should always follow. I'll see if I can get this one into focus. So there's a little negative on the one side here and a little positive on the other side. So you should always follow whatever the indicated connectors are if you can. I mean, it's different for each one. And so I'm basically going to follow that pattern here. So I'm putting the ground, the black connector, here on the top. Oops. So it sort of reset there because it still had some heat. Alright. And as usual, I always put a heat shrink over it. These connectors also have a gold plate on them, which means you don't have to add very much flux at all. In fact, sometimes you can get away without it. The less you pay for your connectors, the more oxide and rust you tend to see on the connector when you buy them, so it becomes harder to solder to them. But these are usually pretty good. I don't think they cost much. I think they're about 50 cents each. Okay, so those are the outgoing wires. Again, that's the male side. The side that actually goes on the battery is going to be the female side. I always try and solder my battery connectors together in case the plastic shifts, because occasionally when you're soldering this, you know, these plastic shells will shift a little bit, and if they're all together, then whatever shifting happens on one side, it will happen equally on the other. So now we want to estimate our length of wire here. And I usually try and have the connector more or less over top of the middle of that battery. And then these wires will go down to the logger right about there. Okay. Alright, so now we just eyeball the connection location here. And we can trim our wires. Again, you don't want excess of wire, you don't want your battery connector floating around too much, but you also, you don't need to shoot yourself in the foot by cutting the wires too short either. There's lots of room here, so I'm not too worried about it. Something else that I always do, whenever I have wires coming through a housing like this where they're likely to see a lot of flexing, I'll put a length of heat shrink tube over the connection point. These plastic holders are pretty soft, so it's unlikely that they would cut through, but when you use the metal battery holders, they have some really sharp edges, and so you don't want your power connector to, you know, eventually wear out and ground or short out onto the battery holder. So I almost always put a length of heat shrink just to protect the bendy parts of the wires. The other nice thing about the heat shrink is it sort of holds the wires in shape. And so you see how that's put a little L bend in there, and it just makes it easier to deal with them later. Don't forget to put your extra little bit of heat shrink. Now this part's a little tricky because sometimes if you take too long doing the soldering, your heat shrink will start to shrink further up the tube. So you want to do this one reasonably quickly if you can. a little close for my fingertips, so I'll try and hold it in place with. It's just a little too much heat in the battery connector for my fingers to hold. Okay. And you can see that the heat shrink's actually starting to melt. I can't get it over the connector because it's too warm. I should have cooled it down a little bit. Still okay. Alright, so now that we have the battery connector and all of the holders arranged, now we can put our logger on the platform. But before I actually adhere it down, I'm going to add all of the extra connection wires and some double-sided tape along the back so that we can stick it down there. So I don't put tape in the middle, I just put it along the edge. And generally 2 layers of tape will get you the thickness that you're after. But depending on how thick your solder job is when you're doing the voltage divider and the other parts of the logger, you may need to add 3 layers of tape.
And the goal is just to get it even, so it'll lie flat?
The goal is to not have any pressure on your connection points. You want enough spacing in the tape that it lifts it off the platform safely. Right? You want it held down, but you don't want to apply pressure to something like a capacitor or anything like that.
Mm-hmm.
The platform itself is ABS, so it does not conduct. You don't have to worry about these pins. It's really just a matter of not hurting your passives like a capacitor or putting pressure on your solder joints.
And what is ABS?
Oh, the chemical name? Something butylstyrene, I think.
And that just means that it's non-conductive?
No, that's the name of the chemical.
Okay.
That type of plastic is called ABS, but forgive me, I'd have to look it up to get the exact.
And is that what makes it non-conductive, or is that?
Almost all plastics are non-conductive. They have to work really hard to make plastic conduct because it's a polymer chain spaghetti, and I think the electrons are bound up pretty well in that spaghetti, so they don't like to move. So it's actually pretty rare to have a conductive plastic. Of course, they make them. I think they dope them with metals or something. Alright, so now we've got some double-sided tape, and you want it to be thick enough that it'll still stick even with all of the items that you've added into the bottom side of your logger. Okay, so I'm just holding it down, and I can tell it's not sort of teeter-tottering on any component. I think, just to be safe, I think I'm going to add another layer on this one. Doesn't quite seem to have it the right thickness, so just to be safe, I'm going to add another one. And again, this is the that was the 5-pound 3M double-sided tape, not the super duper stuff, because occasionally you make a mistake or you realize you need to take the logger off or even replace it because it's failed. So if you use the 10-pound, it gets really hard to take the logger off the platform. Alright, so the next step is to add whatever wires we want for the various breakouts, and this varies depending on what you're connecting to your logger. And as an example, here I've got an I2C connector, and I always use the yellow, white, red, black color standard for my I2C buses. The yellow's the clock, the white's the data, and then power. In this case, there's also an alarm line. Whatever sensor I was hooking up had a 5th wire, so that's a 5-pin connector. There's my LED connector. So red, green, blue, and black. It's a common cathode LED, so it just has one ground line. And these are all of the analog lines on the Arduino broken out. And I've started using this type of connector for driving SPI displays using shift out. So this is a 6-pin connector, which is about the biggest one that I use. This is actually a little hard to solder. So unless you are connecting to a display like I am, or if you want access to your analog lines, if you don't need it, you wouldn't bother adding this wire. This is all optional. So you basically have to decide what it is you're connecting to your logger, and then before you glue it down, it's a lot easier to put the wires in, especially the wires on this side, before you adhere it to the plate. And I just happen to have, cooking show style, a bunch of these wires ready. So now we just need to get those attached. Alright, so on the one side here we've got a couple of grounds. I'm just going to pull that out.
Do you have to tin the wires before you put them in? Or
No, that's a really good question, actually. I used to tin the wires before putting them in, but what I found was that they slowly compressed, and so the solder held the wires together in a thicker package, and then over time the pressure from these little screw terminals flattened them out, and they actually became loose. And if you look at places like NASA, they're very specific about requiring non-tinned wires in a lot of their connection situations. So they want you to not use tinned wires. So no, when you're using screw terminals, try and keep the wires obviously clean, but you don't want to tin them. And the other thing to keep in mind is that you can do what I just did here. You can add more than one wire to the same connector. Because we're going to have two I2C connections broken out on this unit, because you've got the Atlas Scientific and one of the pressure sensors, I'm actually going to break them out separately so you can double up some pins like that. So we're going to do that with the ground. Okay, so there's 3 ground lines that I've brought out with only 2 connectors. And we're going to do the same thing with the data and the clock line for the I2C bus, so that we have the ability to add more connections. Where you decide to put your LED, your indicator LED, depends on your unit. So I usually use 4, 5, and 6. Oops. I'm just going to pull the SD card out there. You want to be careful with these connectors that you don't want them to be loose, but you also don't want to over tighten them to the point that you strip the threads on these little guys. So 2, 3, 4. I've actually got the red here, 5, 6, and 7. On this logger. You'd have to basically set whatever your pins are for your indicator LEDs to match what you're connecting here to. I forgot, I sometimes use pin 4 to power the RTC. Alright. Now if I look under the board here, when we were building this logger, remember we ran the I2C bus up to the clock, and then from the RTC board we brought those lines back down to the bottom. So these are actually power, data, and SCL from the I2C, and we're going to connect those again using double connectors. This is a little unusual, but it's just because you've got this this dual unit. Okay, so we've got the wires already connected to the board. It just makes it easier to do our cable routing later. And as I said, if I was bringing out the analog lines, they're along here, and they would just sort of run along and get bound with this. But I think that's good. So now we can take the tape off and adhere it to the platform. You want to leave yourself as much room as you can. So what I'm doing here is I'm actually bringing this corner to the edge of the platform, because you don't want to pinch all of this space in, so you still have the ability to add those lines later on. So I'm basically just trying to maximize the free space for those wires by putting that connector in place. And you can just push that down and it should stick nicely. Give it a little wiggle. I find that these double-sided tapes need a little bit of movement to finally settle into place. So there we are. And now we're going to use some zip ties and divide these wires out. So I know that, for example, that's the LED. So I'm going to run the LED that way. And it needs a ground line as well. In this case, the ground line is actually on the other side, so I'm going to loop it back and just sort of loosely separate that out for our LED connector. And I usually try and have the zip tie connector on the bottom, because there's more room down here for these things. It also makes it look a little nicer.
Does it matter which ground you choose for LED?
No, they're all common. They're all connected to each other, so it doesn't matter which one you're using. I also do some tricks with my ground wires, so I'm particular about my LED. Oh, I got that one backwards. I'm particular about the limit resistors because I actually use the LED to generate noise when I'm sampling with the ADC. I use it to make noise for a technique called oversampling, which lets you read pretty much any resolution you want. Even though the ADC on an Arduino is not that great, you can add a bit of noise, which I do by pulsing the LED, and oversample to a very high resolution reading. It just uses a lot of power because you have to wait for all of the samples. It's a power of two relationship. Okay, so that's loose. I'm not going to tighten that down. I'm just going to leave that there until I've done my routing. So now we have two separate I2C buses here. These are just going to break out to two connectors. This is the same bus, but I think they all just are going to have to get folded back and wrapped here, and then we'll use some heat shrink to sort of make the wire behave, to make it fold into place. now you can see why I didn't bother binding that other battery connector, because now it's going to be trapped under these zip ties anyway. Okay, so it's loosely in place. Okay. And I usually see how there's a little bit of excess wire there that's sort of folded back. I try and not have it look too ugly, but I leave some so that if there's a pull on a wire for some reason, it hits the zip and there's a little bit of freedom. You know, there's a little bit of slack here that will take out that pull if that should happen. Sometimes when you're working on a logger, you drop it, you know, on the bench or something, and you get a good yank on these wires. Okay, that looks good. And I'm gonna put that down there. All right, so at this point, I usually add some heat shrink, and this just helps with cable management. You can really direct where a cable connector is going to end up inside the logger by just putting a little bit of heat shrink. And it also helps you, you know, keep cables separate from each other, especially if they have similar color patterns. I'm very careful about color patterning, so for example, LEDs always have matching wires to the colors of the LED. But occasionally you end up with situations where your buses have colors that are overlapping, especially if you use a pattern like I do. So the white would be the data line and the yellow would be the clock line, even on different buses. So sometimes it's a little bit hard to tell them apart, and you can put them in different places with this technique. Have to do a little bit of guesswork sometimes to figure out what size is the right heat shrink diameter. That looks like a good, so that size is 4 millimeter. These wires are about 1 millimeter in diameter. This is a 26 AWG silicon wire, and so 4 millimeter heat shrink looks good. You want to be careful that you don't accidentally melt something else in the process. But that just guides the wires to where you want them to be inside. We're going to do 2 more here. This logger is going to have 2 I2C sensors connected through the housing with different wires. That's a little unusual, but it could just as easily be an I2C sensor and an SPI or a 1-wire. You'd still want to do this just to keep your cable management sorted. One at a time here. And you've got a little bit of time to play with when you're shaping the bend, because the wire will retain some heat. Okay, there's one. So those two connectors are going to be relatively close inside the housing. But you can see how that keeps the wires away from the edges. Alright, so now we just have to add the connectors on the end. My current flavor of the month for internal housing connectors are these Dean's micro connectors. I've been using them for a couple of years now, and they're pretty reliable. They're about the most expensive component on the logger, unfortunately. But you know, they do stand up to good abuse, and they come in different colors and different pin numbers. So I tend to use the different colors for different things. So I'll use the red connectors for I2C, and I'll use the black connectors for one wire and the RGB, which is what I'm doing right now. And
why does it have that space in it?
the space is really, really important because that keys the connector so that it can't be connected in reverse. Because if you had power over here and ground over here, and you flipped the connector by accident, you could fry your sensors and do various other bad things. And so having a connector that's keyed like that, it can only be plugged in one way. Very, very useful feature. Some connectors don't have that, and as I said, you can accidentally get them reversed. So I'm just going to add a little bit of flux to the pins and then pre-tin them. See, I created a join there by accident. I'll just flick that away. Just take that away here. This one's giving me a hard time. There we are. Okay, so the pins are tinned, and now we need to get the ends ready on the wire. So you have to have sort of a sense of where you want the wire to be inside the housing. I'm just going to pull this back here. So I know I kind of want this connector to end up kind of over there on the platform. So I'm just going to pull them all together and cut them to that length. And the most important thing to remember is to get your heat shrink on before you connect the wires, because I always forget that and then I have to take it off again. So let's grab a little bit of heat shrink. Alright, and I have a standard connection order that I always use. RGBB, red, green, blue, black. And I can't remember why I first started using that one, but I think it came down to the fact that I could only see certain colors in the dark. So I couldn't tell what my connector colors were in the cave, and I just found this one was the easiest one to deal with. I think it's because in the cave blue and black are identical. I can't remember. As long as you're consistent. The one thing that it does matter is that I use the ground pin on this side of the key, and I use on the other sensor buses, this is ground and that one's power, always right beside this key, so that the power lines can never be switched. This is an LED, so it doesn't really have that issue to deal with, because there is no power line per se. But in the other buses, it really matters. Again, if you should by accident interconnect two different buses, at the very least the power lines will not be mixed up. They're always in the same position. I always use ground on the one side, And again, it's female because the logger is the side that is delivering power. And so, just as with the battery connector, the side that has power is the female side. The same with all of these breakouts. I always make sure that the breakout, because it's supplying power to the light or the sensor, whatever is supplying power, gets the female side of the connector. So on the housings will be the matching male sides. And so now we just repeat the process over again. And because this is an I2C bus, I'll use a red connector in place instead of a black. I'll try and make them different lengths. So this wire is just naturally a little bit longer, so I'm cutting one here and one here, and that way, you know, they won't be fighting for space in the same location inside the housing. But this is a fairly large vertical lump inside the housing, whereas this battery area is going to be flat. So there's actually sort of a lot of three-dimensional space over the batteries. And so I try and have my connections and all the extra bits, like the desiccant packs, for example, they all go here. It's just because of the topography. So you can see that I brought the LED connector over so that it occurs over here. Because if I was trying to make the connection here, it could get pinched between the housing and the vertical rise of the logger itself. So I usually bring the connectors all around so that they happen in this dead space above the battery. So I'm stripping more or less exactly the length of those pins off the ends of the wires so that they match up. One of the things that you find is as you get more practice, you start doing things like that automatically. You don't even really think about it. You just start stripping the right amount of cable. The other thing is, as you get more practice, just generally speaking, your soldering points get smaller and cleaner. It's just a matter of practice. I'm not doing a great job here today, but that's because I'm flapping my gums at the same time. So I have a standard connection order that I usually use, which is on the I2C bus, clock, data, and then again that power connection is always done in this arrangement. No matter what the bus is, I'll have power and ground across that key. So that's our connector breakouts, and again this could be different depending on exactly what you were connecting to your logger. You've got two I2C sensors, and we're going to use different wires for those, which is a little unusual, but it makes sense in the context of what you're trying to build. But there could just as easily have been another whole set along this side of breakouts, and these are just for convenience of changing caps. These are screw terminals. You could just run raw wires into them, but I find that this just makes things easier to deal with in the field, especially when you have component replacements and sensor swaps. Alright, so we will finish the tightening on these and trim them. And then the last thing that we have to do is basically just bring the power line that we had on the platform down and bring the raw and ground wires in to the logger itself. And this is not necessary, but I'm going to run it under that zip tie area again, just for a little bit of cable protection in case it gets pulled on. It doesn't pull right on the screw terminal, it's going to pull on the zip tie hole right there. So just cut it to length, hold it in place, move the wires to where they need to be, and then I'm going to cut them. You know, just basically estimating the length as well as I can. When in doubt, always make it longer than you think it needs to be, but not by too much. I know that's not really helpful, but okay.
Where are those going into?
This is the ground in and power in, the raw power on the logger. Now, because this is a soft plastic edge, again, I'm not too worried about it, but if this was a metal battery holder, I would have done the same thing again on this side. We don't have much risk of cutting the wires. This is a very rounded curve, but if there was a risk, I'd have another layer of protection there. Okay, and you see how the wire sort of comes out and has an S-bend. It doesn't just sort of, I didn't pull that straight and have them coming out at 90 degrees. Again, the purpose of these little zip ties is strain relief. You want all the force to be there, not on the part that's actually connected to the logger. Okay, so that is essentially what we were headed for. You've got your logger from before, from the first set of lessons, and now there's a battery platform and a bunch of connectors ready and waiting for the sensor cap. And let me go get one of those. We'll do that in the next video. This is, you know, this isn't the one that you're going to use on your logger, but this is sort of a typical configuration for me. And on the inside, you can see the connections that would join up. In this case, as I said, it's a slightly different arrangement, but for example, the LED connector is the same, and that lines up with the one that you just added to your logger. And so now we've just made a connection that goes through the housing. And so this is the connector that I was talking about for the display, which we didn't connect. We don't have the analog lines broken out, but if we did, that would plug in here. And then this is a pass-through that goes through the housing, and we're going to talk about that in the next video as well. So you can hook up any sensor you want. In fact, you'll be using this kind of housing pass-through wire
For the Atlas sensor?
For the Atlas sensor. Okay, but for now, you know, we've just basically got what we were after, which is the logger is now able to power itself and we can hook sensors to it.